For thousands of years, people have been fascinated by the number pi. It's more than 2,000 years since Archimedes found that pi is very close to 22/7. In the 5th century AD, the Chinese mathematician Su Chung-chi calculated it to the equivalent of 6 decimal places. Since then, the approximations have got better and better. Now, pi is known to millions of decimal places, thanks to new methods and computers. In this program, we're not interested in how to make such accurate calculations of pi, but we are going to answer the question, what is pi? Or, to be more precise, how do we define pi? Now, this may seem a surprising question. After all, if this disk has radius r, then we all know that its area is pi r squared. So if its radius is 1, then its area is pi. But what do we really mean by the area of a disk? To answer this question, we're going to look at a method used by Archimedes around the year 250 BC. He found his approximation to pi by fitting regular polygons inside a circle, starting with a hexagon. The area of this hexagon gives a very rough approximation to pi, the area of the disk. We can get a better approximation by doubling the number of sides. To give a regular 12-sided figure, a dodecagon. And if we continued this process, we'd get a sequence of polygons whose areas are better and better approximations to pi. And we can work out those areas without knowing the value of pi. Let's see what we get. We start off with a hexagon. To find its area, we divide it up into 6 equilateral triangles. Now, the area of just one triangle is easy. Each side has length 1, and the included angle is pi by 3. So the area of the triangle is a half sine pi by 3. And the area of the original hexagon is just 6 times that, 3 sine pi by 3. Sine pi by 3 is root 3 over 2, and 3 times that is 2.598 to 3 decimal places. Not a very good first approximation to pi. Now, the next polygon has 12 sides. To find its area, we divide it up into 12 triangles. As before, these sides have length 1. But this time, the included angle is pi by 6. So the area of the triangle is a half sine pi by 6. Which means the original polygon has area 12 times that, 6 sine pi by 6, which is exactly 3, a better approximation to pi. Now, there seems to be a pattern emerging here. For the hexagon, 6 sides gives an area of 3 sine pi by 3, whilst 12 sides gives an area of 6 sine pi by 6. And if we continue to double the number of sides and halve the angles, we find that 24 sides gives an area of 12 sine pi by 12. Probably you don't know the sine of pi by 12, 15 degrees, without using your calculator, but it can be found by using the half-angle formulas. And in the same way, you can find the areas of polygons with 48 sides, and with 96 sides, and so on.
So by this process of fitting polygons inside the circle, we've found a sequence of approximations for the area. But what exactly is the area? We've worked out our approximations to 3 decimal places, and we get this increasing sequence of numbers. And it seems intuitively obvious that the limit of this sequence is the area that we need. But how do we know that this sequence really converges? Well, we do know it converges because it's a special case of an important theorem called the monotone convergence theorem. Whenever we have an increasing sequence of numbers which is bounded above, then it must converge. We don't always know what the limit is, but this theorem tells us that it must exist. So here's our increasing sequence of numbers. How do we know that it's bounded above? Well, each of the polygons lies inside the circle, so their areas are all less than, say, the area of this rectangle. So the area of the rectangle is an upper bound for this sequence of numbers. So this sequence is both increasing and bounded above, and so by the monotone convergence theorem it must converge to some limit. And in fact we can use this limit to define the area of the disk. In other words, to define pi, and that's what we wanted to do. But what's the actual value of pi? Well, we certainly know that pi is the limit of this sequence, and so it must be greater than all of these values, such as this one. So this is a lower bound for pi. But it would also be nice to find an upper estimate for pi, as Archimedes did. This time we approximate the circle by polygons from the outside. As before, we start with a hexagon. By splitting it into triangles, we get an area of 6 tan pi by 6. For 12 sides, the same method gives 12 tan pi by 12. And again, there's a pattern emerging. For 24 sides, we get this. For 48 sides, it's this. And for 96 sides, it's this, 96 tan pi by 96. And here's the resulting sequence calculated to 3 decimal places. So by taking exterior polygons, we've got a decreasing sequence of numbers. And each of these numbers is an upper estimate for the area, which is pi. So we can certainly say that pi is less than this last value. In fact, this number is actually 22 over 7 to 3 decimal places, which is the upper estimate that Archimedes got. And we can get a better upper estimate than this by continuing this sequence. Now, it looks as if the sequence converges to pi, but how do we know it converges? Well, it's a decreasing sequence, and it has to be bounded below by the area of the disk, or in fact by 0, because all of these numbers are positive. So it's decreasing, and it's bounded below. And there's a version of the monotone convergence theorem which copes with this. Whenever we have a decreasing sequence of numbers, which is bounded below, it must converge. Again, we don't always know what the limit is. So we know that this sequence is convergent. And it's easy to see that its limit is also pi. So let's put all that together. By looking at interior polygons, we were able to define pi and show that it's greater than this. And by looking at exterior polygons, we got this. So to 2 decimal places, we have pi is 3.14. In fact, we can never write down pi exactly because it's an irrational number. And in order to define pi, we had to use the monotone convergence theorem. Well, there are many possible ways of defining pi, but they all have to use the theorem in some form or another. So how do we prove the monotone convergence theorem? I'm just going to prove the increasing version, that any increasing sequence which is bounded above must converge to a limit. And the decreasing version can be proved in a similar way. Here's an increasing sequence. And here's one of its upper bounds. Now, there are lots of possible upper bounds, But by the least upper bound property, there must be a least one, L. What can we say about L? Well, if we take any number smaller than L, then some term of the sequence must lie above it. And what's more, the sequence is increasing, so all the later terms in the sequence must also lie in this strip. And it doesn't matter how thin a strip we take. Eventually, all points of the sequence must lie inside it. But this means that the sequence converges to L, because if we take any strip around L, from L minus epsilon to L plus epsilon, then there must be some integer n, such that all the terms of the sequence beyond n lie in the strip. So L must be the limit of the sequence.
So the monotone convergence theorem tells us that an increasing sequence, which is bounded above, converges, and its limit is the least upper bound of the sequence. And in the same way, the theorem tells us that a decreasing sequence, which is bounded below, converges to its greatest lower bound. So if a sequence is increasing and bounded above, or decreasing and bounded below, the monotone convergence theorem tells us it must converge. Now we're going to look at another sequence. This time it won't be so clear what the limit is, but we'll be able to use the monotone convergence theorem to show that the limit does exist. This is the sequence we're going to look at, 1 plus 1 over n to the n. How can we tell whether it's convergent? And if it is, what does it converge to? Let's start by working out a few terms to see how the sequence behaves. Well, when n is 1, we get 1 plus 1 to the 1. That's 2. And when n is 2, we get 1 plus a half squared. That's 2.25. When n is 3, we get 1 plus a third cubed. When n is 4, 1 plus a quarter to the fourth, and so on. The terms do seem to be increasing, but is the sequence convergent? Let's look at the sequence diagram. Here are the first 10 points on the sequence diagram. And if we plot more points, they continue to increase. It does look as if they're flattening out, and that the sequence is probably convergent, with a limit less than 3. Now we can prove that it's convergent using the monotone convergence theorem. So what do we need to check? First, is it increasing? And second, is it bounded above? Let's deal with the increasing part first. Well, we can expand 1 plus 1 over n to the n with the binomial theorem, and this is what we get. 1 plus n times 1 over n, plus n times n minus 1 over 2 factorial times 1 over n squared, and so on. Well, n times 1 over n is 1. And we can divide n into this term and this term from the n squared. And that gives this. 1 plus 1 plus 1 over 2 factorial into 1 minus 1 over n, and so on. Well, we know that 1 minus 1 over n is increasing. So this term is increasing. What's the next term? Well, it's n times n minus 1 times n minus 2 over 3 factorial times 1 over n cubed. And once again, we can divide an n into this term and this term and this term from the n cubed, and that gives this. Well, this is increasing, and this is increasing, and so their product is increasing, and that shows that this term is increasing. And in the same way, we can show that the next term is increasing, and so on. And putting all that together, we find that our sequence, 1 plus 1 over n to the n, is increasing. What's the other thing we've got to prove? We've got to show that the sequence is bounded above. And I'm going to show that it's bounded above by 3. Let's go back to our binomial expansion. Well, 1 minus 1 over n is less than 1. So this term is less than 1 over 2 factorial. Similarly, 1 minus 1 over n is less than 1, and 1 minus 2 over n is less than 1, so this term is less than 1 over 3 factorial. And in the same way, the next term is less than 1 over 4 factorial, and so on. So we find that 1 plus 1 over n to the n is less than 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and so on, up to 1 over n factorial. Well, how can we get an upper estimate for this? 1 over 2 factorial is just a half. 1 over 3 factorial is 1 over 3 times 2. And that's certainly less than 1 over 2 times 2, or 1 over 2 squared. In the same way, we can replace each of these denominators by a power of 2. And this is what we get. 1 plus 1 plus 1 over 2 plus 1 over 2 squared, and so on, up to 1 over 2 to the power n minus 1. Well, this is a geometric progression. And we can sum it up and then add in this number 1 to give the following. 3 minus 1 over 2 to the n minus 1. And that's certainly less than 3. So our sequence 1 plus 1 over n to the n is both increasing and bounded above. So by the monotone convergence theorem, it must be convergent. But what is its limit? All we know so far is that it can't be greater than 3.
Yes, the limit's at most 3 because 3 is an upper bound. And it turns out that 3 isn't the least upper bound, so it can't be the limit. The trouble is that this time we've got no geometry to help us, so the limit's not at all obvious. But at least we know that there is a limit, and what's more, because the sequence is increasing, the limit must be greater than each term. So it's certainly larger than 2, or 2 1/4, and so on. In fact, here's the 100th term. So it must be bigger than that as well. We can get closer and closer to the limit by calculating more and more terms. Now, in fact, the limit of this sequence is a very important number in mathematics. It's written e for exponential, and it was studied by Euler, one of the most important mathematicians of the 18th century. To 5 decimal places, e is 2.71828. And it turns out that e is an irrational number, just like pi. Now we're going to use this sequence to define e. That is, e is defined to be the limit of the sequence 1 plus 1 over n to the n. Later on you'll see an equivalent definition. And having defined e in this way, we can then use it to calculate the limits of some other sequences.
Here's one of them. It's the sequence 1 plus 2 over n to the n. We could start all over again, showing that it's increasing and bounded above, and hence convergent by the monotone convergence theorem. But there's a trick which tells us that it's convergent straight away. Remember what we know. We know that the sequence 1 plus 1 over n to the n is convergent with limit e. And we can write that sequence in this way. Now I'm going to write this sequence in the same kind of way, and what we get is this. Well, it's possible to write this sequence in terms of that sequence. This is what we get. Times n plus 2 over n plus 1 to the n. Because you see the n plus 1s to the power n cancel. Well, we know that the limit of this sequence is e. And it's possible to show that the limit of this sequence is e too. How do we do that? Well, we can write this term in the following way. n plus 2 over n plus 1 to the n is 1 plus 1 over n plus 1 to the n. But now we've got a problem, because this n and this n plus 1 are different. However, if we multiply this by 1 plus 1 over n plus 1, we get an extra 1 up there. But of course, we must divide through by the same thing. But now we're okay. These two are the same, and so when n tends to infinity, the numerator will tend to e, and the denominator will tend to 1, because that's a null sequence. So this term does indeed tend to e, and so this tends to the product e times e, or e squared. So we can show that the limit of 1 plus 2 over n to the n is equal to e squared. But what would happen if we had 3 there instead of 2? Well, we can show in the same kind of way that the limit of 1 plus 3 over n to the n is equal to e cubed. And if we had a 4 there instead of a 3, we would get the limit of 1 plus 4 over n to the n is e to the 4th. And that suggests a more general question. What about this sequence? 1 plus x over n to the n. For which values of x is it convergent? And what is the limit? Well, we found out what happens when x is 1, 2, 3, or 4. Let's plot those values. When x is 1, the limit is e. When x is 2, it's e to the 2. And when x is 3, it's e to the 3, and so on. And if we calculated the limit for other values of x and plotted them, the picture would look like this. We seem to be getting a smooth graph, and it's tempting to think that for each x, the limit is e to the x. Well, actually, it's not too hard to prove that the limit of this, as n tends to infinity, is equal to e to the x whenever x is a rational number. But if x is irrational, for example, root 2 or pi, we have a problem. Because so far in this course, we haven't said what is meant by taking an irrational power. However, we can still prove that this limit exists, just as we did when x is 1. That suggests that we use this equation to define e to the x when x is irrational, because we know that it's true when x is rational. So by plotting the limit of 1 plus x over n to the n for all values of x, we get the familiar graph of e to the x. And we'll see later in the course that with this definition, all the familiar properties of e to the x can be verified. In this program, we've looked at a number of sequences. All of them were monotonic and bounded, so we could apply the monotone convergence theorem. And from them, we got some important definitions. First, we saw that using sequences of polygons, we could make a precise definition of the number pi and calculate approximate values for it. Then we showed that the sequence 1 plus 1 over n to the n is convergent, again using the monotone convergence theorem. And we defined its limit to be e. Finally, we discussed the limit of 1 plus x over n to the n. And we said that this limit can be used to define e to the x when x is irrational. You probably already had an intuitive idea about numbers like e, pi, and even e to the pi. But you can define these numbers precisely with the monotone convergence theorem.